Okay, so in this lecture, I'm going to now review the next important set of topics that you may have encountered before, but it's good to go through them one more time just to be very clear about what we are doing here. Okay, so the next topic I want to talk about is the very practical situation where you have taken a single sample. You've done an experiment, you've collected some data, and now you have this one single sample from this experiment. Now we know how to compute maximum likelihood estimates of the sample mean and standard deviation, using the standard formulas that we have. And well, actually the maximum likelihood estimates of the variance is what we compute technically, but I'm going to talk about the standard deviation here. And so now what I want you to imagine is the situation that you repeatedly do an experiment again and again with the same sample size with new subjects each time. Okay, and each time you do this repeated experiment, you compute the sample mean. Okay, so we can simulate this situation, and what I've done here is that I've taken a sample of size 100 from a random variable, a normal random variable with mean 500 and standard deviation 50. I've taken these 100 samples and I can compute the sample mean, which happens to be 502.92 in this particular example. And I can do this again. Oh, sorry, I didn't expect this to move. Yes, so I can do this again with another 100 data points and compute the sample mean again. So I will get a different number each time, right? So what I can do is I can repeatedly run these experiments 1, 2, 3, all the way, I don't know, I can do 1000 experiments, and I can compute the sample mean each time all the way to x 1000. And so what I'm going to get under this repeated sampling scenario is a vector of sample means that's going to differ from one experiment to the other because of random sampling, differences in sampling each time. So here's what I've done now. What I've done here is that I've done 1000 simulations, sample size 100 each time. The true mean is 500, true standard deviation is 100, and I'm going to store the vector of means, this vector of means. I'm going to store it in this vector here called sampling distribution of means. And so I've created an empty vector containing 1000 cells, and then what I do is I run the simulation 1000 times using this for loop. I take a sample of size n, which is 100, and I compute the sample mean and store it in the ith cell of my vector called samp distribution means, right? And so I've also stored the standard deviation just for fun. But what I really am interested in is this repeated, the distribution of means under repeated sampling. Okay. So the interesting insight here, and this is what makes the frequentist approach possible and also fascinating, is that under this repeated sampling scheme, if I plot the distribution of the means under repeated sampling, and that's what I've done here, you're seeing a probability density function of the sample means under repeated sampling. So the big insight here is that the distribution of the means is going to be roughly normal if the sample size n, which was 100 in my simulation, right? If this sample size is large enough, then this distribution is going to be normal. Okay, so what's interesting here is that the underlying distribution, the underlying random variable that I'm getting samples from, does not have to be the normal distribution. So if you look here, what I'm doing here is I'm sampling from an exponential distribution. So the underlying random variable has a support that has a probability density function that looks like this, not like this. Okay, so even then, when I'm sampling from this exponential distribution, the distribution of the means under repeated sampling is still going to be normal. That's pretty fascinating. I think that's a cool fact, and actually that is what makes statistical inference possible. in the frequentist paradigm, right? It's this invariant property of the distribution of the means under repeated sampling, right? It's always normal, right? Regardless of what you're sampling from. That's what makes statistical inference possible, and this property is called the central limit theorem. And the theorem actually states that when your sample size is large enough, the sampling distribution of the mean will be approximately normal, regardless of the underlying distribution that you're sampling from. Okay, so there's a caveat here that this underlying distribution that you're sampling from, the normal or the exponential, it has to have some mean and some variance defined for it. So there is a distribution called the Cauchy distribution, which has the property, oh sorry, this is not written very well. So the Cauchy distribution has the property that it has no mean or variance defined for it. So the central limit theorem doesn't apply in that case. Okay, we are only talking about these well-behaved distributions like the normal or the exponential and so on, right? So the central limit theorem states that the distribution of the means under repeated sampling is going to be approximately normal, provided those conditions are met. Sample size is large enough, and I mean this is kind of vague, but we can live with that, and that the mean and variance are defined, okay, of the underlying distribution. All right. Now notice that what I have here in my picture here is that I've got a vector of means under repeated sampling. Okay, this was in the first simulation also. I had a vector of means under repeated sampling. Okay, so I can now take the vector of means and compute the standard deviation of that vector, right? So that's what I'm doing here, right? If you look here, I've got this vector of means for the exponential that I had, and I can compute the standard deviation of that distribution of sample means under repeated sampling. Now what's interesting is that I started this lecture by saying that you've done one single experiment. Okay, so when you do that one single experiment, the first thing that you typically do is you calculate the sample mean and you calculate the sample standard deviation. So what's interesting is that there is a mathematical result in statistics which states that once you know the estimate of the sample standard deviation, you can figure out an estimate of the standard deviation of this sampling distribution of the means under repeated sampling. This is a very deep idea because what you have is a single sample. Okay, so let me write this down. I've got a single sample. Let's say I have 4 data points. I can calculate the sample mean of this, and I can calculate the sample standard deviation. Let's call it S. This is a single sample. From this single sample, I can get an estimate of the distribution of this means under hypothetical repeated sampling. I haven't done that repeated sampling. I just under hypothetical repeated sampling using this standard deviation estimate and using my sample size, which in this case is 4, I can actually get an estimate of the standard deviation of the sampling distribution of the means under repeated sampling. This is called the standard error. Okay, and there's a closed form formula for this. This can also be analytically derived. Okay, all right. So the key point here is that from a single sample, I can get an estimate of the variability of the means under repeated sampling. That's pretty cool, right? And that's actually what will allow us to do hypothesis testing, as you will just see. Okay, so here's a little example of how this would actually work. I take I take a sample of 100 data points from a particular normal distribution with mean 500, standard deviation 100. I calculate an estimate of the standard deviation, which I'm calling hat sigma, right, from the data that I have. And then given my sample size of n, which is equal to 100, I'm going to compute the standard error, which is an estimate of the variability of the sample means under repeated sampling. This is from a single sample. Okay, that's pretty cool. And this standard error, which is the estimate of the variability of the sample means under repeated sampling, is about 10 here. Okay, all right. So what this means is that from a single sample of size n, I can now figure out the maximum likelihood estimates of the mean and the standard deviation, and I can figure out the standard deviation of the sampling distribution of the sample means. That means the standard error, right, using this formula here. So this standard error is going to be the thing that allows us, along with the sample means, will going to allow us to actually do hypothesis testing. Okay, so this is where it goes now. But before I want to talk about hypothesis testing, I want to quickly review the idea of a confidence interval. So you will often see in papers that we report the sample means with a 95% confidence interval around that, right? And so where that comes from is that the sample means, which I'm calling mu hat here, right, is giving us some estimate of the underlying means that may have generated data. So we can assume that we are going to assume that our data actually coming from a distribution, let's say a normal distribution, with the sample means plugged in as our best guess about what the true mean is, right? What the standard error is doing is it's telling us the spread of this distribution, and more in particular, it's a property of a normal distribution that 2 times the standard deviation of the normal distribution will cover 95% of the area under the curve around the mean. Okay, so the standard deviation of the means under repeated sampling is the standard error, and that's why I've got this term here, mu hat plus minus 2 standard errors gives me the lower bound and the upper bound of what? It gives me the lower bound and the upper bound of the distribution of means under hypothetical repeated sampling. We've just got one sample, and we can draw this picture about what the mean would look like under repeated sampling. That's pretty cool, right? It's kind of bootstrapping information that you don't have. Okay. So it is very common in papers for us to report the sample mean, which is mu hat, with a lower and upper bound mu plus. So mu minus 2 times standard error and mu plus 2 times standard error gives us the 95% confidence interval. So that's how we are going to, report our uncertainty about the sample means. But I want you to think for a few minutes about what this 95% confidence interval actually is supposed to mean. Okay, so in our particular example that we were playing with, we've got some mu, right? So we have the sample mean that we calculated. I don't know why I wrote mu here. I should have written x bar or something like that. I'm very sorry for being a little inconsistent with my writing here. So what is mu here? So I think I've got some hidden code somewhere that I should have made very explicit. But what I'm trying to actually do here is that I have taken a sample, let's say with the R norm function, right? I've got a sample with 100 data points with some mean and standard deviation, and I've saved the vector of scores that I got, and I compute the mean of that vector x, which I'm storing as the value mu. I should have, of course, called it mu hat or something, right? Okay, so I've got my sample mu, and then I'm doing minus 2 times the standard error. The hat sigma I just computed from the data, the sample size I know. So I can figure out this sigma over square root of n, and then if I subtract minus 2 times the standard error, I get the lower bound, and if I add 2 times the standard error, I get the upper bound. So what this gives me is actually a 95% confidence interval, which tells me that my sample mean is whatever this number is, and there's a lower bound here which happens to be 480 here, and an upper bound here which happens to be 520 here. Okay, so if I were writing a paper, and if this was like, let's say 500 or something like that, let's say this was 500, then I would write my sample mean was 500, and then I would write 480 and 520 as my 95% confidence interval. Okay, that's how I would report my results in a published paper or something, right? So, but the meaning of the 95% confidence interval is a little bit tricky. Okay, so what the meaning is the following. If you do repeated sampling, if you take repeated samples and compute the confidence interval each single time, remember that every time you take a sample, you'll get a slightly different mean, you'll get a slightly different standard deviation. Therefore, your confidence interval will keep shifting around a little bit along with the mean, right? So if you repeatedly compute these confidence intervals under repeated sampling, 95% of those confidence intervals will contain the true population mean mu, whatever that number is. In our case, I think it might be 500 or something. So this is what I've done here in this simulation. What I've done is I'm going to compute the lower and upper bound of the confidence interval for whatever number of simulations I had, like 1000 or whatever, maybe 100, I've forgotten. I take a sample size of size n, and then I compute the lower and upper bound each time, right? This mean will differ each time that I take a sample, so you'll have a shifting confidence interval each time. So I can plot this, you know. So first let me plot this and show you. So these are 100 simulations, and what you notice is that the true value of the underlying mu in this example is this horizontal line that you're seeing here. So what is it, 60 or 50? Yeah, it's 60, right? And so of these fluctuating confidence intervals that you're seeing, 5 of these intervals, approximately 5 of them, will not contain the true mu 60, but all the other 95% of those intervals will contain the true mu 60. Okay, and the ones that don't contain the mu are in bold here. You see that? I made those in bold, right? So this is the code that I've done here, and I've shown you also the statistics here showing you that 95% of the confidence intervals actually do contain the true mu, right? So the horizontal line lies within the interval, but 5 or so, 1, 2, 3, 4, 5 exactly, right? Maybe 6, I don't remember. Yeah, there's exactly 5 intervals here that don't contain the true mu. So I just got lucky here. I got exactly 5, but if you run this simulation, you might get slightly different numbers. Okay. Right, so that's the meaning of the confidence interval, that under repeated sampling, 95% of those intervals would contain the true mean, right? So the 95% confidence interval does not have the following meaning. It doesn't mean that the probability that the true value of the mean lies within that particular confidence interval that you got, right, is 95%, right? So that particular interval that you're getting does not allow you to make any probability statement about plausible values of mu. Why is that? The reason is that mu in the frequentist paradigm, the underlying mean, is assumed to be a point value out there in nature. Okay, it does not have any probability distribution associated with it. Therefore, you can't talk about the probability of mu being this or that. Technically, okay, you can't do that. Of course, as a researcher, you might have some beliefs about possible values of mu. That's a separate issue. That's a scientific issue. I'm talking about the pure statistical theory here. The underlying theory of the frequentist methodology is that mu has a point value. It has no probability distribution with it. So you can't talk about the probability, the range over which you're 95% sure that the true mu lies, technically. Okay. So the 95% confidence interval has a very difficult interpretation. Right? And it's hard to understand what it practically means. When you have one confidence interval, what information do you have from this? Well, it turns out that in the Bayesian paradigm, there is an analogous concept called the credible interval, which has this interpretation that we want to give to the confidence interval. So what we want to say, you know, when we compute a confidence interval like here, right? So when I compute a sample mean and I compute the lower and upper bound of my confidence interval, right? So, and I report my confidence interval in this manner here, I'm somehow expressing the uncertainty of the estimate of the sample means, right? And so if I were a pure Bayesian, I would be able to make a statement that I'm 95% sure the value of mu lies between 480 and 520. I can say that as a Bayesian, but I can't technically say that as a frequentist. And so that's a very uncomfortable fact. But sometimes you will find that people actually behave like Bayesians when they're talking about the frequentist confidence interval, right? And in fact, this is not such a crazy thing to do, because for very large sample sizes, the Bayesian credible interval and the confidence interval will tend to look very similar, right? So it is technically incorrect to treat the confidence interval in this way as a measure of your uncertainty of the mean, but we will sometimes be sloppy about that and allow ourselves to think in this way. Okay. All right. So the main point I want to get across here is that we are going to compute the maximum likelihood estimates of the mean, so x bar, which I'll sometimes call mu hat, and we will use an estimate of the standard deviations, sigma hat, to get an estimate of the standard error as well, right? And this allows us to define this 95% confidence interval, which we will in a kind of sloppy way use to characterize our uncertainty of the sample mean. Okay, but really the standard error and the mean mu hat will be used to carry out null hypothesis significance testing, which I'm now going to quickly review. Okay, so what we have done so far is that we have defined the theory of random variables in a very quick way, where we learned about probability mass and density functions and cumulative distribution functions, and importantly we learned how to calculate the probability of observing some value x or something less than that, or some range of possible values. We also learned about maximum likelihood estimation, so we know what the sample means and standard deviation is giving us, right? And finally, we just reviewed the idea of a sampling distribution of the sample means. So this prepares us to talk about null hypothesis significance testing. Okay? Right. So basically, we have a situation now in an experiment where we have a random sample of size n, and the data are assumed to come from some distribution, let's say a normal distribution. Okay, so we can estimate the sample means and standard deviation, and what this allows us to do is that it allows us to describe the sampling distribution of the means under hypothetical repeated sampling. So this is what I've written down here, is what I've been talking about all this time, that with a single sample we can write down an estimate of the distribution of the sample means under repeated sampling. Okay. So now imagine that you take a random sample where each data point is independent from every other data point. So that's what I mean by independent random sample from some random variable. Let's assume that random variable has a PDF, normal PDF associated with it, with some mean and standard deviation. So let's say 12 and 10. And let's say our sample size is 11. Okay, so I just came up with some numbers. It doesn't matter what they are. Okay, so I take my sample of size 11, I compute the sample means, which is 5.47 here, compute the standard error using the sample standard deviation and the sample size, and that happens to be 3.0762 here. So I've got the standard error, right? So the null hypothesis significance testing approach will be to set up a null hypothesis that has some fixed value for mu. So let's assume that we set up a null hypothesis that mu is equal to 0. It could be any number actually. And so what this amounts to assuming is that the true distribution of sample means is normally distributed and centered around 0, right? That's what the null hypothesis is saying. And another assumption implicit in this statement is that the standard error of this null hypothesis distribution is whatever standard error we estimated from the data. Okay. So what we are saying with this statement here is that we are assuming that the truth is that the true distribution is centered around mu with some standard deviation, which happens to be the standard error that we observed from the data. We're just using that estimate to do our inference here. Okay. So what we do is that we set up a null hypothesis distribution, which is the black probability density function you're seeing here, and then we look at the sample mean to see if we land near the center of the distribution or not. Right? So that's the red dot that you're seeing. And so the logic is going to be, if my sample means lies far away from the hypothesized mean, then I will reject the null hypothesis that I set up, right? This null hypothesis. But if my sample means lies close to the hypothesized mean, then I may not reject that null hypothesis. Okay, so that's the basic logic. Now the question is, how do you formalize near and far? The way we will formalize it is that we will talk about the distance between the hypothesized mean mu and the sample mean x bar in standard error units. So what we're going to say is that we're going to compute this distance between the mean and the hypothesized mean and the standard deviation in standard error units. So we're going to compute the number of standard errors t, that the number of units of standard error t that the sample means is far from the hypothesized mean. Okay, so this t value is going to quantify in standard error units the distance between the sample mean and the hypothesized mean. Okay. All right, so what this does is it gives us a statistic to work with, and that statistic is the t statistic. Basically all I've done is I have just divided both sides of this equation with standard error, right? And so I get a t value on the left hand side and x minus mu divided by standard error on the right hand side, and this gives us the t value, right? And so what this gives us now is a number that tells us in standard error units how far away the sample mean is from the hypothesized mean, right? So it turns out that this t value under repeated sampling, right? Imagine that you repeatedly do the experiment, calculate the sample mean each time, calculate the standard error each time, and you compute a t value each time. You could get a distribution of t values, right? So that distribution of t values has an underlying probability density function associated with it. It's also a random variable because it's a transformation of a random variable. Notice that the t value here is actually a function of x bar. X bar is a function of the random variable you're sampling from. So x bar is a transformation of the random variable, right, that you're sampling from, and the t value is a transformation of that transformation. So actually the t value is a random variable that has a probability density function associated with it. What is that probability density function? That is the t distribution, which is defined in terms of the parameter sample size minus 1, right? So it's called the degrees of freedom, and this number, the sample size minus 1, tells you the shape of this t distribution, right? And one important point about this t distribution, and actually I mentioned this one lecture ago, is that this t distribution is no, actually I did not mention this before, I'm sorry, but this t distribution, if sample size goes to infinity, this t distribution becomes exactly the standard normal distribution with mean 0 and standard deviation 1. So now you realize why I was harping on and on about the standard normal distribution, right? The t distribution approximates to that distribution. It's a very important distribution for us for inference. Okay, so we have our single sample and we have our observed t value from that single sample. We know that there is underlyingly a t distribution that observed t value came from, and that underlying t distribution can be drawn theoretically by looking up the t distribution with n-1 degrees of freedom. Okay, so given a sample size, right, given our null hypothesis, we can now draw the t distribution corresponding to the null hypothesis, and then we can compare the observed t value with the hypothesized t distribution, right? If we had very large sample size, because the t distribution approximates the standard normal distribution, we could just use the standard normal distribution, instead of the t distribution. But historically, from a tradition in psychology, we don't do that. We always work with the t distribution. Okay, but I just wanted to be aware of this asymptotic result. When n goes to infinity, the t distribution approaches the standard normal. Okay, so so basically the relationship between the t distribution and the normal distribution can be graphically summarized, right? So if you have 3 data points, right, so n-1 will be 2, the t distribution will have slightly fatter tails than the normal distribution. So in each of these plots, the solid line is the normal distribution, the standard normal, right? The solid line is the standard normal, and the broken line is the t distribution. And you can see that as the sample size, what have I done here? N equal to 3 is what I wanted to say here. In this case, n is equal to 6, right? So n-1 gives you 5. So as you increase sample size, here I've got n equal to 21, right? As you increase sample size, what you notice is that the t distribution kind of starts to approximate the standard normal. And if I kept increasing sample size and kept drawing the t distribution, I would get exactly the standard normal distribution, right? So that's the relationship between the t and the normal that I just mentioned earlier. So the way the statistical null hypothesis testing procedure will work is that I will set up a null hypothesis that my true mu has some value, let's say 0, right? And then given my sample size n, I will estimate the sample mean, the sample standard deviation, compute the standard error, right? Estimate the standard error from that standard deviation and sample size. And then I will compute the observed t value, which is equation 8, okay? And then I will reject the null hypothesis if the t value is large. Okay, so what does it mean for t to be large? We'll just decide that, right? So when we want to now define what it means for t to be large. So what we are going to say is that when I have a t distribution, which is my null hypothesis distribution, which is the solid curve that you see here, what I'm going to say is that I'm going to draw a cutoff line at the two edges of the distribution such that the area to the left of the first quantile here is 0.025, right? And the area to the right of this quantile here is 0.025. That means the total area under the curve in the tails will be 0.05, right? And so what that leaves is a 95% of the area is inside that cutoff range, right? So on this x-axis, I've written t here, but these are t values here, right? So on the x-axis, now I've got a cutoff point here which counts as far away from the hypothesized mean, okay? So if my t value lands here or here outside the rejection points, these vertical bars here, I will reject the null hypothesis, otherwise I will not reject it. So in this particular case, I've drawn a little dot here, which is my sample mean. It doesn't fall in the rejection region, right? It falls within the acceptance region, so to speak, right? And so I fail to reject the null hypothesis in this case, right? Okay. So what we're going to do is we're going to define these critical cutoff points, which are called critical t values. And if our observed t value land is larger on either side, you know, negative t or positive t, then we will reject the null hypothesis, otherwise we won't. So how do I decide what this cutoff point is? Well, it's pretty easy to do this. Now you see the payoff of all that story that I told you about the p norm, q norm, d norm, r norm functions, right? In the t distribution, you also have the qt function, which tells you the quantile such that the area to the left of it is 0.025. Okay, so now you know what is the quantile that gives me the lower bound of that cutoff rejection point for a particular sample size. So sample size is 16 here. That's why degrees of freedom are n-1 here, right? So what this tells me, this function tells me, is that the cutoff point on both ends of this distribution will be minus 2.13 and plus 2.13 for a sample size of 16, right? So I know that it's 16 because n-1 gives me 15 here. So this tells me the critical t value that I have to exceed in order to reject the null hypothesis if I set up my rejection regions the way I just did earlier. This is a mistake here. I wanted this to be like this. Okay, so the reason I've computed the absolute value of the t value is because this is a symmetric distribution, and what I wanted was the absolute number, and I know that the negation of that, the negative value equivalent of that will give me the left edge, and the positive version will give me the right edge, right? That's why I computed the absolute value here, right? Now if I had a larger sample size, if my n was 51, let's say, then my critical cutoff with the qt function would be a value closer to 2, right? So what will happen is when you have sufficient data, large amounts of data, your critical t value will approach 2. Okay, that just happens to be the case because the t value will approach, the t distribution will approach the normal distribution, and about 1.96 is the quantile for the standard normal distribution. So what I mean is that if you have a standard normal distribution with mean 0 and standard deviation 1, the 95% of the area under the curve is going to lie between 1.96 and minus 1.96. That's just a property of the normal distribution. Okay, Center point is 0 here. So this is 1.96, and minus 1.96 is basically close to 2, right? And so that's the equivalence that you're seeing between the t distribution and the normal distribution as you increase sample size. Okay, so we can be a little bit sloppy and say that we will always assume, assuming that we have lots of data, which we typically do, right? We will assume that our critical t value is approximately 2, right? So we don't actually do this calculation every single time in this course, is what I mean. When we are actually studying t distributions and so on, we can roughly just assume that, plus minus 2 can be a critical cutoff point for rejecting the null hypothesis. Okay, so that's how I often do quick analyses without actually using the QT function, because I know that for large sample sizes it really doesn't matter. All right, so so what I'm doing now is I'm actually walking you through the logic of the t-test now. So I have my null hypothesis mu, right? I've got some sample mean, some sample standard error. I can compute the observed t value, and now I can decide whether to reject the null or not. As I just said, my critical t value is 2 approximately, so I'm not going to reject the null. I can't do it, right? It doesn't mean I accept the null, but I fail to reject the null here. Okay, all right, so I already explained all this. For large sample sizes, t will be approximately 2, the critical t, so we can just fake it, so all this I've explained. So I think I can skip all this because I already talked about this now. And so what will happen in real life is that you will have some, let's say you have some independent and identically distributed data, some vector of scores, right? And you will do a one sample t-test, and you can extract the observed t statistic, which is just the same number I just showed you earlier, which I computed by hand, right? Here, I computed this by hand. The t.test function is actually doing the same thing for you, and it will also show you that if you ran this entire function standalone, if you wrote t.test and just wrote statistic, it would give you a bunch of output, which we'll look at in the next lecture, which tells you the full story of the analysis. But here I'm just printing out the observed t value because I can just look at it and decide whether to reject the null or not. Here I'm failing. I failed to reject the null. Notice that I'm being very careful, and I'm not saying that I accept the null. I just failed to reject the null. Failing to reject the null does not mean that you can accept the null. Not necessarily. Okay, so we'll get back to that later.